Hi, it's Haley. I'm here to go through the 2018 AP Physics C free response question number 2. We'll start by going through and defining key terms and variables that we'll be using. We'll start off with mass. Mass is given by the letter M, and typically we use the units kilograms. So that's what we'll be using. And we'll define mass as a measure of inertia, which is the resistance to change in position or speed that an object has. If an object has greater mass, it has greater inertia, so it has greater resistance to change. And then we also have a variable t, which means time. And this can be denoted with a lowercase or uppercase t. It's kind of interchangeable. And then typically we'll use seconds for the units here. It's pretty obvious. I think we know what time is generally. And in physics terms, it's kind of the interval in which change happens or change occurs. And then moving on to position. Which is denoted by the letter X, and we will use meters in M for position. And this one's pretty obvious. Position of an object is kind of where a particle is with respect to an axis. So it's also known as a displacement or distance. We can use delta X, meaning change in position. So X is the displacement of an object. And as I just said, we also have this symbol. Delta is given as a triangle, and that symbolizes change. Pretty simple. If you have delta x, that means change in position. If you have delta t, that means change in time. If you have delta v, that means change in velocity. Next, we'll talk about velocity. Velocity is denoted by the letter v, and it's given in the units meters per second. Or m/s. And velocity is essentially the speed of an object. Velocity is the change in position of an object over a change in time. So we can define velocity using the equation v is equal to delta x over delta t, which we know means that velocity as a function of time is equal to the derivative of its position. Velocity is essentially an object's speed with added direction, so that means that it is a vector and it possesses both direction and magnitude. Moving on, we'll go to acceleration. Acceleration is denoted by the letter A, and it's given in units of meters per second squared. Acceleration is the rate that speed changes with respect to time, and like velocity, acceleration is also a vector. It has magnitude and direction. And then the equation we can use for acceleration is A is equal to the change in velocity over the change in time, as acceleration, as I said, is the rate that the speed changes. And we know that from our integral calculus is equal to the acceleration as a function of time is equal to the derivative of velocity as a function of time. And then now we'll get into force. So force is denoted by the letter F, and it's given in units of newtons, which is the letter N. And force, pretty simple, is a push or pull on an object. And the equation for force is F is equal to ma. As I said before, m is equal to mass and a is the acceleration. So the force on an object is equal to that object's mass times the object's acceleration. And as I explained before, mass is a measurement of inertia, which is resistance to change. So with more mass, there's more inertia, greater resistance to change. So from this equation, we can see that there would be more force necessary to create the same acceleration on a greater mass. If mass increases, then the force needed to move that object increases. And then likewise, if we have an object and there's more force exerted on the object, then we have a greater acceleration. And force is also a vector, meaning it has magnitude and direction. And then we have several equations on the equation sheet that relate these variables. I'll write them out here if you don't have that equation sheet with you. Alright, so we can see from these three equations, if you have two of the variables, you can find the third variable, and these relate time, acceleration, velocity, and position of an object. And these equations are known as the kinematic equations. And we can see there's some subscripts here. When we see the 0 subscript, that means not. And that essentially means the initial. We can also use a subscript of I. So then this one would have a subscript of F. It's not quite written in, but this is essentially here the initial or the final position minus the initial position. And so here would be the initial velocity, because it has the 0 subscript, meaning not, and then this would be the final velocity, and same for at the top equation. Okay, moving on to momentum. Momentum is denoted by the letter P, and its units are kilogram meters per second. And momentum is given by the equation P is equal to mv. We know mass is equal to m and v is equal to the velocity of an object. So the momentum is equal to the mass times the velocity of an object. It's essentially a measure of how much mass is in how much motion. And again, momentum is also a vector. It has a magnitude and direction. And from momentum, we can go into conservation of momentum. The law of the conservation of momentum states that in an isolated system, then the total momentum in that system remains constant. There's no added momentum. So the initial momentum is equal to the final momentum. In other words, P initial is equal to P final. And then if we look at this equation, if we look at a change of velocity, which means a change in the speed of an object, we would also see a change in momentum, and we can write that as delta P is equal to M times delta V. Before we wrote out this equation here, A is equal to delta V over T, and if we switch that around, we have delta V is equal to A times T. And then we can plug that into this equation right here. Delta P is equal to M times A times delta T. And then if we see this here, M times A, as I said before, Newton's second law of motion says F is equal to ma. So then we can go and see that this is equal to delta P is equal to F delta T. And this brings us to impulse. Impulse is denoted by the letter J, and its units are Newton seconds, or NS. And impulse is the change in momentum. So J is equal to delta P. As I said before, momentum is P. So then we also have J is equal to F delta T. And we can see here that this means that J, or impulse, is equal to the integral of F with respect to T. So that means that impulse is the area under the curve of a force versus distance, of a force versus time graph. And we'll come back to that really quickly when we start looking at the question. Let's talk about the spring constant. Spring constant is denoted by the letter K, and its units are newtons per meters, or N over M. The spring constant is a measure of the stiffness of a spring, meaning that it's a measure of how hard it is to stretch or compress a spring. So if it has a greater spring constant, that means it's a stiffer spring, so it's harder to compress or stretch that spring. With the spring constant, we have another formula, which is F is equal to negative kx. And in this formula, we know F means force, and x is the displacement or distance that the spring is stretched or compressed from the equilibrium point, which is when the net forces on the spring are equal to 0. And then really quickly, we'll talk about energy. We have 3 types of energy. We'll start with kinetic energy. Kinetic energy is denoted by, there's a few different forms. We'll use KE in this tutorial. You can also simply use K, and its units are in joules, which is the unit for energy. And kinetic energy is essentially the energy of motion. So when an object is moving, when it's moving through the air, when it's rolling down a ramp, if it's in some kind of motion, then it has kinetic energy. And that energy is given as the equation KE is equal to 1/2 mv squared. We know m is equal to mass and v is equal to velocity. And then moving on to potential energy, we have, first let's talk about potential gravitational energy. And that is given as, we'll use P, E with a subscript G, and its units are as well also J, or joules. And potential energy is the energy stored in an object due to its height or relative position above a zero. So this is given as PEG is equal to mgh. And I haven't talked about G or H yet. Really quickly, G is gravity. Here on Earth, it's negative 9.81 meters per second. It's an acceleration. So if you drop an object, it falls at the acceleration of gravity. And then height is h. Pretty simple. It's just the distance above a relative zero. And then we'll move on to potential elastic energy. And potential elastic energy is given as PE with a subscript E for elastic, and its units are also joules, as is all the energy units. And potential elastic energy is the energy stored in typically a spring once it has been deformed, so either due to a stretch or a compression. And that equation is given as potential energy as PE subscript E is equal to 1/2 K times delta X squared. And we just talked about K. K is the spring constant. It's the measure of how stiff a spring is, and then delta X is the distance that it has been either compressed or stretched from its equilibrium. Okay, so let's talk about the center of mass. So center of mass is given as cm. And it can also be denoted as x subscript cm or y subscript cm to mean the center of mass in the x direction or the center of mass in the y direction. And the equation for center of mass is the parts of the mass times its position divided by the total sum of mass. And we can write that like this. And so that means that if we were to have a circle or a square, the center of mass would be in the middle. It's the point on an object or a system of objects in which the mass is equally distributed on all sides. Okay, great. We can get into the problem now. We'll look at this AP Physics C Mechanics Free Response question. I'll read through the question and draw a diagram here for us. So we have cart 1, and then we have cart 2, which has a spring attached to it, and we'll label cart 2 as M2. And we can see that in this problem, cart 1 has an initial velocity, so we can say V naught of cart 1 is equal to 3.00 meters per second. And it is moving to the right. So we see that cart 1 has an initial velocity moving to the right, whereas cart 1 has an initial velocity of 0. And I'm using subscripts of initial, which is I. But if you see a 0 meaning V naught, that also means the initial velocity. And then we have a K, which is the spring constant of this spring here. And then I'll go ahead and write out all of our given information right here. We have M1 is equal to 0.500 kilograms. M2 is equal to 1.05 kilograms. Initial velocity of cart 1 moving to the right is 3.00 meters per second. And it's important that we see here that we defined moving to the right as positive direction. And then K is equal to 130 newtons per meter. So as well as these variables, we are also given a equation for force and a graph for force versus time. And we can see the equation is 3,200 newtons per second squared times t squared minus 500 newtons per second t. Let me write that out. So in this problem, we also know that there is negligible friction. We do not have to take into account the friction on the train tracks. We simply have this problem of cart 1 or M1 going to the right and engaging in an elastic collision with M2. And the first question, question 2A, says, using integral calculus, calculate the total impulse delivered to cart 1 during the collision. And I just explained impulse. Impulse is the change in momentum, or the integral of force over with respect to time. And so we have the force equation here. From the graph, we can see the time interval that is given, which is from 0 to about 0.16 seconds. And so for question A, we can go ahead and say that impulse, which is equal to J, is equal to the integral of 0 to 0.16 of this equation here. And assuming that those watching know how to do integral calculus, we can just go ahead and take the integral of this and then evaluate it from 0 to 16. So let's do that. Okay, so we took the integral and we got negative 2.03 newtons per second. And that is what we have for impulse. That's the total impulse delivered to cart 1 during this collision. So moving on to part B, which asks us to calculate the speed of cart 1 after the collision. So we can denote that as we're looking for V of cart 1 final. And we just found impulse, and as I said before, impulse is the change in momentum, and momentum is given as m times v. So if we have the impulse and we know the change in momentum, we'll be able to find delta v, which is the velocity final minus velocity initial. And as we know, velocity initial of cart 1 is a given in this equation. So we can start off by saying delta p, or the change in momentum, is equal to J, which is equal to what we just found, negative 2.03 newton seconds. And that is equal to M1 times V1, or M1 times delta V1, which is equal to M1 times V final minus V initial, which is equal to the mass of cart 1 times the velocity final minus the velocity initial. And we have M1 and we have V1, so we can go ahead and plug in those values that we have and solve for V final. And we have our answer. The velocity final of cart 1 is equal to negative 1.06 meters per second. And again, we have this negative, which makes sense because if we look at the problem, we have cart 1 moving initially in towards the right, which we defined as the positive direction, which means that after it hits the spring, it will bounce back and move in the opposite direction, which in this case, since we defined positive direction as right, the negative direction means left, which gives us the answer for B2. So number C is asking us to calculate the speed of cart 2 after the collision. We just found the speed of cart 1 after the collision, and we know both the speed of cart 1 and the speed of cart 2 before the collision. And as we know from the conservation of momentum, that the momentum before the collision will be equal to the momentum after the collision. There are no external forces in this system, meaning that momentum is conserved. So momentum is given as P, which is equal to mv. And by the conservation of momentum, we know that P initial is going to be equal to P final. And P initial will be given as the total momentum before the collision. So that would be the momentum of cart 1 plus the momentum of cart 2. And we can write that as M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. And we know that cart 2 was not actually moving at the beginning, meaning that V2 initial is equal to 0, and that this means that we can cross this out as that is going to be equal to 0. And so we're left with M1 V1 initial is equal to M1 V1 final plus M2 V2 final. And we know all of these values except for V2 final, which is what we are trying to solve for. So we can plug in our values and solve for the velocity of cart 2 final, or after the collision. And from this, we will get our result as 1.93 meters per second, which again makes sense considering that the final cart of the final velocity should be positive, meaning that cart 2 will be moving to the right as cart 1 collided with cart 2 and moved it to the right. For part C2, show that the collision between the two carts is elastic. So elastic collisions mean that not only is momentum conserved, but energy is conserved. Elastic is, in this case, a spring. There's a collision in which the masses do not become deformed and bounce off of each other. And to show that this is elastic, we'll go with the key characteristic that energy is conserved, meaning that the energy before the collision will be equal to the energy after the collision, or the initial energy is equal to the final energy. And we can start with saying that the total energy initial is only kinetic energy. We have one cart moving towards the other cart, and there is no potential energy stored in either a height or a spring. The spring in this problem is currently at equilibrium. It has not been compressed yet. So for our initial energy, all we have is the energy of motion, which, as we defined earlier, is kinetic energy. So we have kinetic energy initial is equal to the total energy after the collision. We know that not only is cart 1 moving, but also cart 2. So then we have the total kinetic energy, meaning the kinetic energy of cart 1 plus the kinetic energy of cart 2. As before, I said that kinetic energy can be given as the equation 1/2 mv squared. So then we can write this as 1/2 m1 v1 initial squared is equal to kinetic energy of cart 1 after the collision is 1/2 m1 v1 final squared plus the kinetic energy of cart 2 after the collision, which is given as 1/2 m2 v2 final squared. And we have all these values. We need to simply prove that energy is conserved, meaning that both sides of this equation are equal. So we can go ahead and plug in our values and solve to see what both sides of the equation. And then right off the bat, we can see that the 1/2s all cancel out, so we can just cross those off. And then we will get that the left side of this equation is equal to 2.25 joules, and then the right side is equal to 2.24 joules. And the values are not exactly the same number. They're very, very close. And we can say that this small difference is due to rounding errors in our math. And so that this still shows that the equation is an elastic collision in which energy is conserved. Okay, so part D is asking us to find the speed of the center of mass of the two-cart spring system. So it's not asking for the center of mass of one cart, of cart 1 or cart 2, it's asking for the center of mass of the system. And as I explained before, the center of mass is in which the mass is equally distributed on both sides. It's a point of balance. And however, in this problem, it would be very hard to use this equation that I gave to calculate the position of the mass at any given time. And so we can also use a different equation, because we know that in this two-cart spring system, energy is conserved and momentum is conserved. And we know that momentum is equal to P times, or momentum is equal to P, and P is equal to M times V. And so we can find the speed or the velocity using that equation. So if we're looking for the center of mass, for the velocity of the center of mass, we can denote that as V subscript Cm, and we know that total momentum in the system is equal to the total mass in the system times the velocity of the system. So we can write that out, m total times v. And this v here would be the velocity of the whole two-cart spring system, which is the velocity of the center of mass of this system. So that is what we were trying to solve for. And so if we rearrange this equation, we get the velocity is equal to p total divided by m total. And we know from the law of conservation of momentum that the total momentum initially is equal to the total momentum final. So we can say that P total is equal to, either we can use the initial or the final momentum, and in this case we can use the initial would be easier since it is simply just the momentum of cart 1, so we can just say m1 times v1 initial, and then the m total and then the total mass of the system is simply mass 1 plus m2. And then we can go ahead and plug in these values that we know and solve for the velocity. And then we get here the value of 0.97 meters per second for the velocity or speed of the center of mass. And then finally, for part 2 of D, it asks us to find the maximum elastic potential energy stored in the spring. So we can start off by just saying we know that the potential energy of the potential elastic energy is equal to 1/2 k times delta x squared. And so if we're trying to find the max potential energy here, that would be the max value of this equation. And since k is a constant, all we're trying to find is when delta x is at its max. So that would mean that when the spring is compressed to the maximum distance that it can in this problem. And we know that the maximum compressed distance will occur when there's a maximum force applied to the spring. So we're trying to find max distance, which is at maximum force. And since we have the force equation, we can just use the derivative of this equation to solve for when that is equal to 0 to find the maximum of this equation. So if we go ahead and do that, so then we get that the maximum force is at when t is equal to 0.078 seconds. And then we can just plug that right back into this original equation that we had for force to find what this maximum force is. And then we would get that this maximum force is negative 19.5 newtons. And from that we can use Hooke's law to find the maximum distance that this applied force would compress the spring. So Hooke's law is given as F is equal to negative kx, and therefore we have negative 19.5 is equal to negative, and then we can plug in our value for k, which we wrote at the top as 130 Newton meters times x. And then solving for x, we get x is equal to 0.15 meters. And that's the maximum distance that this spring will be compressed. So then we can go back to our equation for the potential elastic energy, which is equal to 1/2 kx squared. X and delta x we can use interchangeably here as saying that the change in distance of the spring is going from equilibrium to the maximum distance, which is 0.15 meters. So then we can say that this is equal to 1/2 times 130 times 0.15 squared. And then we get potential elastic energy is equal to 1.5 joules. And that is our answer for this last problem. Thank you for watching. See you in the next video.